The next problem that we have to solve is one about the graph of f shown below. So, looking at part A, we have to suppose f is a function and suppose that g of x is equal to x times our function f evaluated at x squared. So, referring to the graph above, we have to compute the derivative of g of 2. So, the first thing we want to do is work out what g prime is. So, we know that g of x is equal to x times f of x squared. So if we take the derivative, we're going to need to use a product rule here. Remembering that our product rule is f prime of x, g of x, plus g prime of x, f of x, whenever we're taking the derivative of f times g. We're going to do something very similar here. The derivative of x is just going to be 1, and then we're going to have the derivative of, and then we're going to multiply in our f of x squared. Next, we keep the x and we multiply in by the derivative of f of x squared. So we're going to get f prime of x squared, but there's a hidden chain rule in here because of this x squared. So we get the derivative of our x squared inside, which by the power rule is 2x. So overall, our function is now going to be, for g prime of x, we get f of x squared plus 2x squared f prime of x squared. So in order to evaluate this, we need to know what f of 4 is and what f prime of 4 is when we plug in our g prime of 2. So we come up to our graph and we mark out at x equal to 4. We're going to have the point for 0, so that will be our f of 4. And we look at the slope of the line because we're looking for the derivative. To find the slope of the line, we could just take our rise over run and find out that the slope, which is equal to f prime of 4, is -1. Plugging those in, we do our final calculation to say g prime of 2 is equal to 0 plus 2 times 2 squared times -1, which is equal to -8. Looking at part B, they say let the area of x be equal to the integral from 0 to x of our function. So, looking at A2, we could rewrite that as the integral from 0 to 2 of our function. Remember the area of, or that the integral is just the area under the curve. So, looking from 0 to 2, that would be bounded by this red box that we're looking at here, 0 and 2. So we have area up here that's going to be positive, and we would have area down here that's going to be negative. So I would say a good way to work this is to think about it as splitting it into 2. We can say from 0 to 1, we know we're going to have f of t dt, and we can add to that everything we get from 1 to 2. Important to note in this problem is that we can actually solve this pretty easily through just some geometry rather than actually doing the integration. Because these are triangles, we know that their area is 1/2 base times height. Both of these triangles have a base of 1 and a height of 2. So, since 1 is negative and 1 is positive, we know they're going to cancel out and give us 0. If we're looking at a prime of 3 for part 2, we're looking at the derivative of our integral. So another way of thinking about it would be to write it as d dx of the integral 0 to x f of t dt, which is f of x, and we want to evaluate that at x equals to 3. So looking at our graph, f of 3 is going to be the point right here, which is 1. Finally, we're looking at a double prime of 1. The same way that we just saw a prime of 3 was just the function, we can say, hey, I know that a double prime of 1 is the same thing as the derivative of my function at 1. Remember, a prime went to just the function, so if we take one more derivative, we just show up with one more derivative right here. So, Coming up to our graph at 1, we say the slope of this section of our line is going to be approximately 2. Looking at the next page, we want to compute the following derivatives, and we don't need to simplify them, so we want to make sure we don't waste any extra time on that step. So we have y equals to sine of x divided by 4x. Because we see division, the first thing we have to do here is either quotient rule or rewriting it such that we have 4x to the negative 1 power. Either way would be a viable option for solving this problem, but we'll do it with the quotient rule just to make sure that we are remembering that one. So quotient rule says that we need to take the derivative of the top times the bottom minus the derivative of the bottom times the top, all divided by the bottom squared. Taking those derivatives, the derivative of sine is cosine. The derivative of 4x is 4. And the square on the bottom is 16x squared. And we're done. Next up is we need to take the derivative of the square root term. So we want to be careful here because square roots we want to rewrite as fractional exponents. So rewriting f of t as t squared plus 3 to the 1/2 power gives us then a chain rule here. So the chain rule on this one says that we need to take the derivative on the outside as if it was just t, so we would have 1/2, whatever's on the inside, to the 1/2 minus 1, and we'll drop it down, t squared plus 3. Since it's not just t, we have that chain rule, we have to make sure and tack on the chain rule term, which is the derivative of t squared plus 3, everything in the middle. Writing that out for our final solution, we get t squared plus 3 to the negative 1/2, and we get 2t. On the next one, we have another composition of functions, so we're going to have another chain rule here. We have to be a little bit careful because that's going to be tangent inverse, not tangent to the negative 1 power. So they are slightly different. So tangent inverse, we want to remember, is the same thing as arctangent. And the derivative of arctangent is equal to 1 over 1 plus x squared. We can get that from the book or we can memorize it either way. It's a good one to be familiar with. So doing the exact same thing we did a second ago, we're going to take the derivative and say that we have 1 over 1 plus whatever's on the inside of that arctangent. In this case, it's not x like we had earlier. We have cosine of x. So because it's not just x, we need to tack on our chain rule term. So we'll put a little CR to remember it. And we're going to say that the derivative of cosine is negative sine of x. So with that, we're done. The last one is we have a function that is another composition with now secant and the natural log. So our important trig formula here is to remember that the derivative of secant gives us secant of x, tangent of x. So doing the exact same thing we did earlier with the chain rule, we're going to go through and we're going to say, okay, the derivative of secant gives me secant of whatever was on the inside, tangent of whatever was on the inside, and we notice it's a natural log on the inside. The derivative of the natural log gives us 1 over x. So we tack that on to the very end, remembering that it's theta here in this problem rather than x, something to be keep a watchful eye on. And we're done. Biggest thing on any of these derivatives is just going to be remembering your chain rules because that's the easiest place to miss something.